So if you guys are ready, we'll get started back with Tim Fowler. Tim's another close friend, met at a BSides in Asheville, North Carolina. Last year we met and hung out and turned into really good friends. Tim got me educated more on software-defined networking while we were there. It's interesting conversations, but Tim is really big into wireless sensors, wireless networking, wireless security, monitoring, coming up with new innovative, creative ways to hack and monitor wireless networks. Lives up, like I said, lives up in the North Carolina area, and come down here today with us to share some of his new recent research. Y'all help me welcome Tim.
I'm probably the least qualified person that has spoke today, but I am very grateful for this opportunity. I do want to thank Paul, Dynetics, all the BSides Huntsville staff, everybody that helped put this on. This has been a fantastic event, especially if you were here yesterday for training. All the talks today have just been fantastic, so really honored to be here. So today we're talking about a DIY approach to building a sensor network. I thought I'd do a really clever title called Sensory Perception. That's the best part of the entire presentation is the title. So now y'all can have fun with that. A little bit about who I am. Obviously Tim Fowler. I'm a security consultant for a small firm in Asheville, North Carolina. You can find me on Twitter at Rubix. 2 O's, 2 X's. A little bit about me. I'm a Christian. I'm a proud member of WNC InfoSec, which is our local information security group in Western North Carolina, Proverbs Hackers. I have my OSWP, which I only put that in there just to give a little bit of credence to the fact that I somewhat know what I'm talking about with wireless. Big open source advocate. I love everything about Wi-Fi. It is awesome. It's so much freedom, so much convenience. And for the same exact reasons, I loathe and hate Wi-Fi. Good luck trying to secure a wireless network against me. And I'm actually, believe it or not, despite my size, I'm a triathlete in progress. And so that's my background. In order to kind of understand where we're at today with this talk, we've got to do a little bit of a history lesson where everything started. And it really started a couple of years ago with a couple of projects. If you remember, and I believe it was 2012, Black Hat, Brendan O'Connor released a project called Creepy Doll in conjunction with F-bombs, which were essentially disposable sensors based off of Raspberry Pis. Some really, really cool stuff. The idea was just to be able to see what you could see on the airwaves and different things like that. And then a little bit later, we got a project, originally Snoopy from SensePost, and the new iteration called Snoopy NG was released this summer. They took it up a level. Back at Black Hat Asia, they put a sensor on a drone because why not? You know, it's one thing to be able to have surveillance on people, but let's do it from the air. And the answer to why would you do this? Because you can. That's the answer for most of the hacker cultures, that we just do these things because we can. But these were really cool projects that kind of got me. My entire background is in wireless. The first time I ever actually hacked anything or broke anything was gaining access to a wireless network. It went steadily downhill from there. But that's where my roots are, and I stay true to those. So I've always had this background in wireless. And so when I started kind of seeing this concept of these sensor networks and looking at what you can do from a wireless perspective just from the airwaves, you know, how many people have ever put a wireless interface in monitor mode? Okay, a good many of us. And it's like, it's cool, you see all these access points and stuff like that. Like, the amount of data that's just freely there has always intrigued me. So from these kind of projects that have always sat in the back of my mind and different things like that, I started mulling over them and stuff. And from these projects, I was challenged last year by Paul Coggin, actually, to write a presentation for Hacker Halted. And I was like, all right, cool, yeah. And so I go to the website, look at the CFP. The theme for Hacker Halted 2014, the zombie apocalypse. I'm like, okay. I was like, I got to figure out how to write a presentation to survive the zombie apocalypse, and my strong suit is wireless technology. The result, actually, was quite successful. I came up with a presentation called When Zombies Take to the Airwaves. And the whole premise was that we have people with smartphones, they become infected, and we now have zombies with smartphones. And I lay a lot of hypothetical, theoretical situations. The concept was that we're in a city where we have a massive wireless infrastructure that has been deployed to provide internet access to our citizens. Well, in the moment of the zombie apocalypse and stuff, immediately that service that we're providing to the citizens in this wireless access and things like that, from the data that we can see in that entire network, we're actually being able to make decisions, predictions, trend forecasting as to what's going on in near real time in the zombie apocalypse, simply using wireless data. And it was really cool, really far-fetched. I was really kind of shocked when the Register ran an article on my presentation from BSides Augusta. I found out 2 days later. The only reason why they did it was because The Walking Dead was going to start back in 2 days, and it was clickbait. I still take it, But what's to say? Marketing good publicity is any publicity. So it was cool. A lot of fun from a conceptual standpoint. But I got one question over and over and over and over again, and that was, have you ever done this? And the answer to that is sort of. I have messed around with wireless for a long time. The concept of sensors is not something new to me. I've played with Creepy Dog, played with Snoopy NG, as well as a few other just one-off designs and stuff like that. But I've never really sat down and done a wide-scale mass deployment or anything like that. And so 2015 rolls around, I'm going, I need to talk. I need something that I can present a couple of times. Let's actually do it. Let's take the theoretical from last year, When Zombies Take to the Airwaves, and let's actually do this. And so that's where we are today. And so getting into the crux of the presentation, we're going to be talking about a brand new project called the Harbinger Sensor Network. And I chose Harbinger for a very specific reason, and you'll kind of understand this when we get into the objectives of this project. But it's a person or thing that announces or signals the approach of another. Pretty simple, but it's very fitting name for an actual sensor network or sensor project. So in the rest of the presentation, you'll see HSNP, which is just Harbor Sensor Network Project, or I'll say Harbinger, a bunch of different things. It's all the same stuff. So I had two fundamental objectives in starting this project. The first thing is I actually needed to have an end goal, something that I could accomplish in terms of that actually makes the project viable, and not just answering because I can, but I actually wanted to accomplish a goal. So the first thing I did is I want to create a distributed sensor network for data collection and traffic flow / migratory pathway analysis. That's a bunch of terms. Basically what I wanted to be able to do is look at how devices move through three-dimensional space. And by looking at and analyzing that data, it allows us to create a predictive model the same way that we do weather forecasting and the same way that we do migratory predictions for migratory species such as birds. Essentially, it's just looking at trend analysis, and thus we're able to make some predictions based off of all the historical evidence how devices are going to continue to move through the network. So, for example, if I inject an environmental variable, such as, let's say, a roadblock, statistically I should be able to figure out how people are going to deviate based off of all the historical data. That was one of the core objectives. The other thing is I wanted to create an analytic engine for data processing and visualization. Any big data people here? No, a couple. What's the fundamental thing for big data? You got to show it off. Got to have a pretty dashboard. Got to have this nice visualization that looks good in the boardroom and things like that. You've got to have a way of digesting the data. And so that was one of the core objectives to this project as well. The why of this, obviously, is because I wanted to continue the process from last year's talk, but ultimately it's because I can. I've got enough experience in this. I've got enough context and information that's like, why not? This will be fun. But as I indicated, there are other projects that are already doing this. There are sensor networks that you can go, specifically Creepy Doll, SensePost. In fact, SensePost has just announced or released back in January a commercial offering of Snoopy NG, which is really, really cool. I've had some conversations with some of their developers and stuff. Awesome people, great project. But I don't want it to appear to see if I'm reinventing the wheel. To me, this is more like a Lego set. You buy a Lego set, it's got all the building pieces. You make what the instructions say, and then the hacker way, we tear it apart and we build something much, much cooler. So I'm using a lot of the same components and the same concepts, but the end result is really, really different. So some more information about the project. It is a wireless sensor project for historical trend and predictive analysis. That is its primary objective. Can you use it for something else? Absolutely, and I will let your mind figure out what those purposes are. Unlike other sensor projects, Harbinger is a completely passive system. This is key. It is it's passive. There's no transmission. There's no interaction with the clients whatsoever, which is good because then you have a pristine data set. It also means that in an age of maybe that data collection is not so popular within the public eye, it makes it almost impossible to detect. And big thing for me is Harbinger is a fully open source project, and that means that it has an open source license applied to it, which actually gives you all the rights to do the code, to manipulate the code, take the project, run with it, and it is licensed under the GPL v3. If you're not an open source person, that's not going to mean much to you. I'm very passionate about open source, especially in this industry. So I had some requirements, must be open source. As soon as this presentation is done, the code will be released. So we'll check that off. Must be as hardware agnostic as possible to keep costs down and allow people to use whatever hardware they have available. There should be an asterisk on this because that is a core objective and I failed miserably. And we'll talk about that in just a second. The solutions are coming. I did want to keep the dependencies and requirements to a minimum. It's easy when you start doing data collection and you start parsing packets and stuff like that for your code to get really, really convoluted, and you have all these dependencies of different modules and extensions and all this other stuff. So in order to actually run the code, it's a 4-hour process of just installing all the tools and stuff like that. I wanted to keep it absolutely as minimum as possible. The biggest thing that was left is it must scale. This is a 1 sensor system, and this is a 10,000 sensor system. Okay, it just works. However you can deploy it, however you want to deploy it, whatever your need is, it scales very, very well in its current form. And as we continue down the development pipeline for this project, it's going to get even better. So this is something that you can take the code and immediately start playing with on your laptop and stuff like that. The project breakdown, as I said, this is an ongoing project. It's not complete. There's 3 primary stages, which is the first stage is you've got to have a means to collect data. So the sensor nodes are very important, and that's and then stage 2 is you've got multiple nodes, large scale deployment, hopefully, because everybody's going to go and deploy like 10,000 node networks because we can, and you guys are rich. We need a way of managing the data in a uniform fashion. One thing that eventually is I will actually be writing an API so that everybody will be able to access my data. It will be sanitized, but for analytics purposes, making the data in a uniform way, an easy management system. So that's stage 2 of the project. And stage 3 is where really the bread and butter of everything. Being able to capture the data is cool, and that's what we're mostly talking about today, but it really comes to stage 3. Being able to use the data to create a form of intelligence, being able to make predictions, look at the historical trends and things like that. after the last couple of days of going through Rob's introduction to threat intelligence and Edward McCabe's open source intelligence talk today, what I've basically realized is what we're seriously talking about is wireless threat intelligence, which is a really cool concept that not a lot of people have talked about. So stage one, the sensor nodes, that's where we're at today. That's the code that's being released today, and what we're going to spend the primary rest of the talk on. So there's a few requirements for this particular project that you have to have in order to run the code. You must be able to run Python, specifically 2.7, which means basically any hardware that you've got. SQLite 3, there again, minimum requirements, and a wireless interface that supports monitor mode. You don't even have to support packet injection, which means you have a lot more chipsets that are available to you, because here again, it's a completely passive system. We're not interacting with anything in the network. All we're doing is turning the ears on and listening to the airwaves. So there are some hardware suggestions that you can kind of use. Obviously, the one that comes to mind for most people is going to be Raspberry Pi. Really cheap, cost-effective. Actually not the perfect system for this, but it's really, really well. You can use the A, the B, the B+, and now the 2, which I'm really excited to get a couple of those in and actually try this stuff out. The increase for CPU performance is going to help a lot. BeagleBone Black. TP-Link MR3040, and there's an asterisk to that by that. And simply because this is my ideal platform, because you can't deploy this. Somebody's going to find this, somebody's going to see it, it's going to draw a lot of attention to it. But what I can deploy is this. Okay, this is a TP-Link MR3040. It's running OpenWRT. It's got a 2,000 milliamp batteries, which means you got a self-contained power source, which means I can get about 5 hours of wireless sensing out of a single device without an external power. And it's $35. It's cheaper than a Raspberry Pi. The only thing that you do have to do is you do have to have a USB drive for an overlay file system, and as well as your data storage. So all in all, you're looking at under $40 for a self-contained unit. The reason that there's an asterisk on this is I did most of the development work on this in one infrastructure and design with the chipsets. And so I'm going to give you the cliche answer. Well, it worked on my box. When I started porting the code actually over to this platform, the AR71XX series chipset has some issues with the current code, and you just get junk. So I've got the solution for that. It's just not quite ready. But within about the next week or so, this is going to be the perfect platform, because there's nowhere that you can't deploy this. Little double-sided tape, just stick it somewhere, whatever. It is a great unit. Also, if you are worried about data collection, the concern about data collection and the public fear and stuff, if somebody finds this, it's no big deal. It's $35. And the best thing, as it sits right now, it doesn't tie back to you at any point, because there again, it's a completely passive system, which kind of stinks to a degree, because you do have to manually retrieve the data currently. Coming up in the future, I've got a solution for that as well. Also, the TP-Link TLWN722N, very awesome wireless adapter. It suffers the same problem as the internal chipset. Solution for that's coming, but really cool. So basically, any hardware that you've got that can run Python, SQLite, and a monitor mode, you can set up as a sensor. So from a laptop to an actually dedicated deployable sensor, you can do that. So in order for this to be a sensor network, we've got to collect specific data. If you are very familiar with 802.11, there is a ton of data in the airwaves. Lots and lots and lots of data. We're only looking for specific pieces of data. We're not collecting the entire packets, because that's not really feasible for data storage and stuff. Some of the things that we're looking at is I'm wanting to detect client probe requests. Any client moving through the network that's looking for anything. I want to be able to capture that. I need to see what time the device appeared in the network. I'm also looking at the time that it left the network. and this is from an individual node's perspective and the collective network. I need to see if it's interacting with any APs. Specifically, I need to see the probe responses of the APs. The time in which the responses come in is very important, as we'll get into. And so this is just a little bit of a subset of the data that we're looking at, but we're not collecting a tremendous amount. We don't need a tremendous amount because with these few individual data points, the amount of analysis and deductions that I can make from a data set is astronomical. It will absolutely, once you actually see the entire platform by the end of the year, it will blow your minds the kind of correlations that we're able to make simply off of this little bit of information. So this is currently how the data scheme looks in the SQL like database. There will be some modifications to this coming up as I fine tune the requirements in the data. But mostly what we're doing is we're capturing, as I said, the client MAC addresses, the access point BSS IDs or MAC addresses, and we're looking at the correlation between those points. Anybody familiar with Wiggle? Wiggle ward driving app? Okay. So Wiggle is an awesome thing. I really, really like that project a lot. I do wish they'd open up their API a little bit and not so restrictive. But so what Wiggle does is it allows you to map all of the access points that are in your given area. Well, what we're doing is this is what I call the inverse Wiggle. Instead of just mapping the access points, we're actually able to map all of the devices that are broadcasting on 802.11 in your range. All of them. Not just access points that are in master mode. Anything that's broadcasting, we can see. So this is kind of the data structure that we're having. There again, if you look at it, it's very limited in what we're actually capturing. We're not capturing who you're talking to in terms of like what's web services or anything. And that's one of the differences that Harbinger has versus some of the other projects is they're actually analyzing, going down into into the packet level, going who are you talking to, what type of device is it, is it coming from an iPad version 3.1 or whatever. They're looking at the model numbers. They're actually analyzing the traffic. I don't care about the traffic. I just want to see what is present in my network. So where do you get started? And the first thing you have to do in this instance is you have to get the code. It's funny. Which is not currently available. It will be at the end of the day. You'll be able to find it. It is on GitHub. They're, again, open source guy. If you write code, if you write a project, please publish it. Please. Even if it's really bad. I'm publishing some really bad stuff at the end of this talk. It works, but it's probably really, really bad. If you're like a hardcore Python, please don't look at it. But it's because the thing about what I have figured out, especially in this industry, if you write a tool, publish it. You never know if somebody's going to need it or you're going to solve their problem. And it's not up to us if that's the solution for them. I don't get to choose if this is your solution. I can just put it out there, and if it is, you get to use it. If not, so please publish your code, and that's my PSA for now. So in order to actually get started, and I did not update my slide properly, you'll be able to clone the Git repository, CD into the directory, and you can run Harbinger SH. Specifically, there's actually two methods that you can do. Harbinger SH it already goes and puts the interface in monitor mode for you. It's using like IW and ifconfig. The other option is if you don't have those tool sets in your environment, you can simply use something like if you install the AirCrack suite, AirMon NG will put your wireless interface in monitor mode, and then you can just directly run the sensor code. So this is a snapshot of what the sensor code actually looks like. It's only about 240 something lines. It's not very complicated. It is written in Python. I will say that I have a new dear friend, Adam Byers, who basically he wrote the original code for this for one of his projects, and he was gracious enough to let me take that code and run with it. And so I would never have been able to do this without him. So thank you, Adam. Absolutely, really, really cool. So this is just kind of what the code looks like, and if you care about that. This is the DB, which is nice. It's allows us to actually query the database and pull out the information, and we can do it based off of access points, probes, clients, and data. So I will tell you, there's a couple of reasons I'm not actually going to demonstrate the code. One, because it's going to detect everything in this room. And also, just out of respect, I don't know what the restraints of this facility is and anything like that. And so it's just out of respect, I'm not going to actually turn on a sensor. But what I can show you is this is what the data looks like coming out of the actual node.db. This is the database file. This was a scan that me and my good friend Switch did last night, standing on the side of University Drive. I'm out there with a little Chromebook and this little antenna doing my best Statue of Liberty impression, capturing this data. And I was really worried when the cop went by and his brake lights came on. Luckily, nobody stopped. But this is what the code looks like in terms of the database. And if I can jump over and pull this over, yeah, we're in there. We will actually just look at some of, I can't see. Yeah, so these are some of the clients that I detected. I did a 5-minute run on a single sensor. I had 78 unique clients, 195 unique access points with almost 30,000 packets that we actually parsed, which is so much information. And this is from a static node. And you can see this is the data that we're looking at, and this is basically giving us the correlation of who is talking to who at any given point. And we can go through all this, lots and lots of information, lots and lots of data. These are actually the probe requests. Here we're able to see what the SSIDs are, which comes in that comes handy in just a second as we actually solve some of the problems that deploying a sensor network presents. Looks basic. The structure is basic. If anybody understands 802.11, the data that's being presented right here is very, very powerful in terms of you start doing this from 1 node to 2 nodes to 3 nodes to 4 nodes and start scaling this up and deploying it. Being able to get all this information and looking at where devices are and where they're passing through the network is so huge. So let me get back to the presentation. It'll let me. Yeah, so this is how the output of the database looks right now. And coming up in stage 2, what I've actually already started on it, we'll have a mechanism that will allow us to sync all of the individual node databases into an aggregate system for processing, which is going to be really good because just looking at this individual data from a 5-minute scan is kind of boring, and it's kind of hard to come up with any real estimate of, well, honestly, anything, because this is just a snapshot. But understand, like anything, when you're dealing with data, time is your best friend. The longer you can collect data, the more you can collect data, the more statistically relevant information that you can get out of it. And that's ultimately what the goal is. If you want to play around with this for like an hour, you're going to have some fun. It's a cool, little thing to do, but it's not going to render you much results. The thing about this is the success of a sensor network is simply the longevity and the amount of data that it can capture. And once you have the data, then it's up to you as to what you do and how you process it. So let me get back into the presentation mode. So you have a node or multiple nodes. You went out to and bought like 1,000 of these things, and you've got the code all set up and stuff. Now you're ready to deploy your sensors. First of all, there's a few things that you have to look at when you're trying to figure out where you're going to deploy. First of all, you got to figure out what you're going to cover. Like, do you want to cover the entire city of Huntsville, Alabama? Okay, we're going to have to do a little bit of planning because Huntsville's kind of big, and actually it's kind of long, especially down University Drive. So you're going to have to kind of figure out how big your coverage area is going to be. However, once you figure out what your coverage area is, there's an important question that you have to ask. Do you need 100% coverage in terms of, I want to cover 40 square miles, which is a ridiculous amount for a sensor network. Do I have to cover 40 square miles in wireless detection? Does anybody know the answer to that? No. I absolutely do not have to cover 40 square miles to capture a statistically relevant amount of data. Are you going to collect 100% of the data? No, absolutely not. Because of the nature of wireless, you're gonna miss things. A lot of the sensors are running low power, low performance CPUs, which means if it can't process it, it just drops it eventually. So you're not going to get 100% of the data, but you're going to get enough, and especially over time, that you're going to be able to make inferences based off of what you are missing. So there's some questions that you have to answer when designing, and I call it the grid, even though most likely it's not actually going to be like a square grid. In your deployment, it really does become a grid. So some questions that you're going to have to ask is, where are the choke points? People understand the concept of a choke point in terms of like traffic or herding or anything like that. Choke points are simply a path where people have to go through. A mall, for instance. If the entrances and exits, those are choke points. Okay, let's say I want to deploy this at a mall. I don't have to cover everything in the mall. I just need to cover the entry and the exit points at a minimum, because then that way I've got traffic coming and going, and from that I've got time correlation where I can extrapolate a lot of the additional information. So you don't have to cover 100%, but you do have to identify the key points in and out of your coverage area that have to be covered. If you've got a main highway coming into the section that you're trying to monitor, guess what? You need a sensor there, and you're going to need one on the other side, making sure, but you do not have to get 100% coverage, because one of the things that the data is going to allow us to do is it's going to allow us to fill in the gaps. We're going to be able to mathematically calculate some of the missing data. Another important thing is, can a device be seen by multiple nodes? Okay, if the node coverage overlaps, this is a very good thing for us, because it gives us more additional information at the same point in time. Because if node A and node B can both detect device A, it gives me a correlation. But it also, when I move forward, say 30 seconds in time, node A cannot detect device A, but node B is still detecting. I now have movement. I can mathematically determine at what rate of speed the device is moving through that network and in which direction. So having overlap, it's not required, but if you can design it that way, it is awesome. Also, you need to make sure you have some resiliency in your network. What happens if a node goes down? Okay. In most cases, in most deployments, because you're going to be constrained mostly from a budgetary standpoint, what's going to happen is you're just going to lose some data accuracy, because one of your choke points is no longer going to be covered. Now, if you do have a perfectly designed system and an infinite budget where all of the nodes are overlaid so that two nodes can always cover what a single node covers, then you've got redundancy within your network and you're never going to miss anything. It's not cost effective and stuff, but these are things that we've got to look at in terms of our deployment, simply because it really comes down to a budgetary, a time, and infrastructure standpoint. So depending on how expansive your coverage area, it will dictate what requires for your grid. This is actually a little snapshot from close to where I live. It's approximately, I think it's 480 square acres or something like that. I don't remember. But let's say this is where I want to cover. And this is a really interesting place because the streets are laid out not in a grid fashion, but they're also not like super windy. You've got a lot of right angles and things like that, which maximizes the efficiency of our nodes and stuff like that. So first thing, identify where you want to do this. Another thing that I figured out that is super, super important is before you ever deploy a node, you have to figure out what's around. You need to know what the 802.11 infrastructure that you're dealing with is. So my recommendation is to go out into your coverage area, start running Wiggle, start running Kismet, find out what's around you. You need to know everything that's around you because specifically Wiggle and Kismet, where you're looking for access points, you're going to use those access points to fine-tune the placement of your nodes. So the node placement, you want to determine the exact area. You need to estimate where the choke points are in your grid that will require coverage, and you need to test at those. At each of those locations that you require a sensor for entry, for egress and ingress into the grid, you need to test the wireless landscape right there, and you need to cross-reference it with Wiggle. So what we're going to do, I'm going to take my node out, and I'm going to turn it on, let it run. I'm going to take the data, and I'm going to look at the access points specifically. And I'm going to see every single access point that this thing could detect. I'm then going to cross-reference the Wiggle database for the same geographic location. And it's going to create an overlay. And what it actually does is it produces an ERD, an effective range of detection. By overlaying the Wiggle data versus what our sensor can see, I can determine with fairly high accuracy how far my sensor can actually see. Because what I do is I see this Donald Wi-Fi network on both Wiggle and on the sensor. Well, Wiggle provides me the GPS coordinates. I know how far away from my sensor that is. So it may be 50 feet, it may be 150 feet. But what this does is allow me to figure out in that topology and that landscape right there that this particular sensor is effective at approximately 172 feet. Okay, well that's good because that means I need to start placing my next sensor somewhere around 160 feet away. And the result of calculating the ERD, and for me, I thought this was a brilliant solution for solving this because I could just put a sensor every 50 feet and spend a lot of money. Or I can figure out what the effective range. It also allows you to change hardware configurations. If you've got a little better antenna configuration that's a little more power, a little higher output, you can put that in a strategic location, which then it gives you the ability to have a multi-architecture sensor network, but it's performing the same task. So the result is, instead of just covering every single choke point, as well as a few key internal areas, by calculating the ERD, I'm able to reduce the number of sensors by about 30%, which is a huge cost savings. If you figure average cost of a sensor is going to be about $50, it's a pretty effective thing. And this is because we're looking for maximum efficiency for lowest cost. Because I'm not a millionaire. I don't make a lot of money, so I need efficiency. And it makes it more readily available to deploy. And it also, if things happen, they're easy to replace. You're not, the last thing you want to happen is deploy a massive sensor network and then something go wrong and you lose half your sensors and you can never afford to replace them. Because then the project's completely useless. It may still be completely useless depending on your application, but it's definitively useless. So your ERD is highly variable and will frequently change. Things such as weather, topology, as well as material composition of the surrounding structures. Steel, concrete, things like that will play a big role, and stuff. So these are some of the things that you got to take into consideration for your actual deployment of a Harbinger network. Briefly mention the last two stages. Stage 2, which is coming down the pipeline, it'll probably be ready sometime in June. The centralized data management, and will also contain the API in which people will be able to access. I don't have a lot to say about this, and it's not fancy, it's not cool, it's just an absolutely necessary component of this project because I don't want to sit here and have to drive around to every single sensor and start pulling USB drives and offloading them. Although, with this device right here, I can set up a hidden wireless network that my system can automatically connect to. So as I drive through the network, my system is whitelisted in the access point on this device, as soon as my MAC address hits this system, it automatically starts an SCP to my local machine. That's one solution that I've already got in place with these. So, but you can do this however you want to. Like I said, centralized data management, not sexy, but very, very important for this project moving forward. And then the third thing is the analytics and data visualization. I stumbled on how I'm going to solve some of these problems the other 2 weeks ago on Twitter, of all places. Somebody retweeted this link, and I jumped down the rabbit hole, and I spent 3.5 days programming in R for the first time ever. Anybody use R for statistical analysis and stuff? Wow, that is amazing. R with RStudio and Shiny, so much fun. So I actually have a visual framework that I've already started mocking up. But it looks something like this. Now, naturally, there's not any data points on here right now. But what it allows us to do is I can drill down into a specific region, meaning if I have multiple networks deployed, and I will be able to select an individual node, or I can do groups of nodes, or I can do the entire network. And from that, I'll be able to kind of get a bird's eye view of what's happening in the network, but I'll also be able to run predictive algorithms based off the historical data and also show those as overlays. So if I want to look at the historical trends of a single device over the last 30 days, I'll be able to do that. Or you guys will actually be able to do that. The visualization and analytics platform is scheduled for, I'm hoping to wrap it up late August and fine-tune it and probably deploy sometime in October. The analytics will actually be a standalone platform simply because it has a lot of value for other data sets, especially if we're in Edward McKay's open source intelligence. Some of the stuff he's doing, those data feeds and threat data feeds would pipe directly into this system, and you'd be able to actually see visual representations of stuff. So this is, like I said, this is an ongoing project. It's going to take me through the rest of the year to actually complete to get where I want to. At each stage, there'll be new announcements, new releases. Everything will be completely open source, so you can go and play around with it and stuff. The actual analytics platform will be a web-based system, so as soon as it's up and ready, you can actually go and start running your own calculations. You'll have the ability to put in your own R programming algorithms and actually run that against my data set. So it'll be really, really cool. Because I like wireless, but I like data more. So when I can combine the two, I get really excited. And so this is the introduction to the Harbinger Sensor Network project. I'm really excited to be able to release it specifically here at this event. So that, like I said, this is coming soon. And that is all I have. Is there any questions, comments? Haters need not apply. Yes. Yeah, so the question there is, have I tried any triangulation? And the answer to that is no. Oh, trilateration? Well, essentially, yeah. So trilateration, in this case, the answer to that is actually yes. I don't have it in the code for a few specific reasons, but yes. So the question is, have I done anything with trilateration? Yes. That's where the access points become really important, because the access points aren't, for the most part, are not moving. Okay, they're static entities, so is my sensors. So if I've got a device that is moving between one node to another, I have at least 3 points of hard data, static data, node 1, node 2, and any access point that's in this detection. From that, based off of the time differentials, the deltas of time in which the packets are sent and when their detection, as well cross-referencing the actual geolocation data of all of those data points, I can actually detect and calculate at the speed that they're moving, but it also gives me the ability to replay that over time. So I can actually go scrub back 30 days and watch a device, like just imagine like a scroll bar of a video and just replay that entire movement. While I only know that they were here and here, mathematically I can assume they definitely went to the center location. So yeah, there is a lot of that that is taking place. I just understand that to a degree, that high level of accuracy of knowing there's a device in this within 3 feet of something is really creepy to most people. There is one element to this that I didn't talk about in the next version of the sensor code that'll be out probably in the next week or so. I'm adding one more piece of data that makes this even a little more creepy, and that's I'm capturing the RSSI of the packets, and I have found a formula that will accurately help me determine within 2 feet of the access point where you're at. So now I can, from the other data, I can know whether you're obviously in range of the node. From the RSSI, I will be able to determine how far you are from the epicenter, directly from that node. Now, I still don't have east, west, north, I just know you're in this area. But because of node overlay and the other node being able to pick you up, I know now I can determine if you're on the left side of the sensor coverage or if you're on the right side or the north side or the south side. There again, things that I'm only collecting a small data, but it's the correlation between the individual points that becomes really, really powerful. Because understand, this is all metadata. It's all metadata. At no point are you personally actually identified, but there's enough to do it. So, and I also, if anybody's ever interested, I have solved the MAC randomization for Apple in this network as well. Because that's actually a real big problem when you have MAC addresses that are getting regenerated all the time. There's actually a solution for that that's coming as well, which is kind of cool. So, any other questions? Awesome. Thank you guys. You've been awesome.